In the last video, we took a look at Newton's third law of motion and saw that we could use it to help identify forces that might be a little tricky to figure out their direction, among other things. So here I want to just take a brief moment to talk a little more about gravity and weight. So let's say we just got a box fall into the earth. So we can go ahead and do a force identification diagram for it. And if we neglect air resistance, there are no contact forces. So the only long-range force we have will be gravity, which, as I've said before, I prefer to write as F sub g. I'll get into that in just a second. Now, it is a correct model of things to say that the gravitational force that an object feels is equal to its mass times g. Now, this g here, so this is object's mass, and this g here is what's called the local gravitational field strength. Now, we don't really need to get into what fields are just here. That's something that we'll get into more when we study electricity and magnetism. But here, suffice it to say that this summarizes everything that a planet is doing to the object. Planet's influence on objects. When we go and take a look in a few videos' time at things like orbital motion and stuff like that, we'll have a more fully developed model of gravity, and we will be able to compute this little quantity, little g, anywhere we would like. But it turns out that if you're within 11 kilometers of the Earth's surface, this quantity is equal to 9.8 newtons per kilogram, and this would be good to within 1%. Now notice I wrote the units as newtons per kilogram. Most books, heck, most people will write it as meters per second squared, and sure, if you plug in that a newton is a kilogram meter per second squared and you cancel that kilogram, you would get meters per second squared. The reason I prefer to write it this way is that, again, when you go and study fields much later on, you'll find that this is a typical way of writing field strengths, is force per charge, if you will. And here, the object's gravitational mass is effectively its gravitational charge. So I like doing this just to remind myself of a very important fact. And this, whoops, sorry about that. And this is that g is not an acceleration. And this is even despite many people calling it the acceleration due to gravity. It's really not that. So what it really is this gravitational field strength. And usually in a lot of intro treatments, people get really sloppy about that. I tend to be a little more pedantic about it, mostly because I'm trying to avoid certain misconceptions developing that I really am afraid to even state lest they take root. But for pedagogical reasons, I prefer to keep this distinction very clear. Now this value of g does vary with altitude. So as an example, at the height of the International Space Station, it's actually kind of easy to remember. It's 8.9 newtons per kilogram, not 9.8. So the farther away you get from the Earth, the weaker it is. You get up to where communication satellites are in orbit, it's a little over 0.2 newtons per kilogram. So it's a lot weaker up at those altitudes. It also depends what planetary body you're talking about. So for instance, if you're on the surface of the moon, the value for little g is about 1/6 what it is here on the surface of the Earth. But there's sort of a handy way to remember whether this 9.8 number is good or not. Since this 9.8 number is good to within 1% if you're within 11 kilometers of the Earth's surface, that turns out to be pretty much the altitude by where either a person or a machine can breathe oxygen. So, or breathe air. So basically the extreme heights of what supersonic aircraft can fly at. If you're within that range, g is this value. Now there's no causal relationship between the air and this value or anything like that. It's just one of those happy coincidences that makes it easy to remember. So if you're looking at a problem, if either either a person or an aircraft could operate by ingesting the local air, then g is to within 1%, 9.8 newtons per kilogram. So what about that whole acceleration due to gravity being 9.8? Where's that all coming from? So if we go and take a look again at our object falling down, so I draw my free body diagram like that. Let me go ahead and draw in a coordinate system here. We can start to express Newton's second law of motion for this object. So let's just do that. We remember from Newton's second law of motion that the acceleration will be the net force over the mass of the object, where this mass, remember, is the inertial mass. Now here, this will be equal to the gravitational force over the mass, since the gravitational force is the only one there is. Now if we take y components of this, a here would equal, since gravity is pointing down, this would be minus fg to account for going down over the mass. But we said that fg is minus fg would be minus mg. This would be a sub y here over m. Now keep in mind, remember this m here is the gravitational mass. This m here is the inertial mass. And we cancel these, even though they're technically different things, because we're pretty darn sure they're equal, and to our best ability to measure, they are. So we go ahead and cancel them. And now what you're left with is that numerically, the acceleration of a freely falling object is numerically equal to minus g. So then at that point, yeah, sure, if you want to take your newtons per kilogram and turn it into meters per second squared, that's good. A lot of people sort of just lump all the steps together, but the reason I keep bringing up that g is not an acceleration is, let's take a look for a second and say, what if instead of us just having our box drop, let's say it's got a parachute. So here's my box, here's my parachute. We'll say the parachute just opened. So here we can again draw a free body diagram for it, but now what we've got is we'll have the force of gravity down, and we'll have a force of drag up. So here again, so if I'd say the acceleration is equal to F net over m, here the net force is going to be the vector sum of these two. So this will be d plus fg as a vector. Now let's take the y components of it. Here d is pointing up, so this will be d, and fg is pointing down, so we'll write minus fg over m. So if I distribute it out, this will be d over m. Oops, sorry, ay equals. This will be d over m minus mg over m. Again, keep in mind that these m's are technically different, but we cancel them anyway. What the point is that this is very much not equal to 9.8 meters per second squared if we're near the surface of the Earth. Or negative, I should say. We're going to get some number that's closer to 0. So the acceleration, the magnitude of the acceleration will be less than 9.8 meters per second squared. And we can create situations where it's more. So that's why I harp mightily that g is not an acceleration, despite how many books tend to write it in an honest attempt to try to deconfuse the situation. I'm afraid that sometimes that might be creating more trouble than it's worth. Alrighty. So with all of that in mind, let's talk about the term weight. I'm really not a big fan of the term. I am aware of research that has been done where the researcher went through pretty much every college level textbook written in English, and there are hundreds of them. And the researcher took a look at the different definitions of weight that were being used. What they found was that you could lump the definitions into 6 different definitions. 2 of them were extremely rare, and another 2 of them were pretty darn rare. But there was, so basically, if you look among the books, there's a 50-50 split in definitions. The one is what a lot of books will also just call the apparent weight. So this is what a scale reads when you stand on it. Oops. Now, if you think about that for a second, if you're standing on a scale, you've got the normal force of the scale up on you, you've got the force of gravity down on you, and what the scale reads is the normal force that exerts on you. So this is really, sorry about that there. There we go. This is really measuring the normal force. Okay. The other definition, which is used about 50% of the time, is the gravitational force. due to a planetary body on an object. Well, this is just gravity, right? So there's a 50-50 split. The physics community is not agreed, does not have a universal agreement on the definition of the term weight. And even when you see books that say, and when we say weight, this is the one we mean, a lot of times when you go digging through the problems, they'll just start chucking the term weight around and wind up meaning the thing that was other than the one they said that they were always going to mean with it. So when you see the term weight in a problem, what you want to do is figure out which of these are we talking about, and then call it what it is. So this is why I like writing F sub g instead of W. Also has the added bonus that we're going to run into a quantity called the work later, and so that makes it notationally a little less confusing. But my attitude is if you just call it what it is. So if you have a problem where they talk about the weight of something, look at that problem, decide whether they're asking for the apparent weight or the gravitational force. And then if they're asking for the apparent weight, then we're talking normal force. And if they're asking for gravity, then we're talking gravity. So since we have universally agreed upon definitions for normal force and gravity, use the terms that are universally agreed upon. Okay, so as you might guess, I'm also not a fan of the term weightlessness. So what's going on with that? Well, when we get to orbital motion, if we say look at the International Space Station, and let's make it a satellite. I can't draw the International Space Station. So if we were to look at, say, some satellite orbiting the Earth, those are supposed to be the solar arrays. So it's orbiting the Earth like so. What we're going to find is, again, if I do a force identification diagram on my satellite, we see that there are no contact forces. So when I draw a free body diagram for it, what we get is just the force of gravity from the planet acting on the satellite straight down. So that force of gravity is since force of gravity is always directed to the center of motion by Newton's second law, and it's the only force, it means the net force points to the center, which means the acceleration also points to the center. And we've already seen earlier, if the acceleration is always perpendicular to the motion, you go around in a circle. So quite literally, when a satellite or anything is orbiting the Earth, it's actually continuously falling, but it's moving sideways so fast because it's of its tangential velocity. And it's moving sideways so fast that the Earth always keeps curving out from underneath as it's moving around, and so it always misses the Earth. So in other words, in Douglas Adams' series of books From the Hitchhiker's Guide to the Galaxy, in So Long and Thanks for All the Fish, we learned that the way that you fly is to fall to the Earth but miss. That turns out to be exactly how things orbit. They're always falling to the center of the Earth, but they're always missing. So, since you are always falling, your apparent weight, you wouldn't feel any normal force pushing up on you, right? There is no normal force, so you look at the diagram. So they tend to use the term weightlessness here referring to the apparent weight, because there's no normal force or anything like that. If you were to stand on a scale, it would read 0. And so by that definition of the term weight, you would be quote-unquote weightless. But because of the fact that not all the physics community is not universally agreed on that term, NASA coined an alternate term which also has its problems. They like to call it microgravity. And I'll say that that's less objectionable, but at, say, the height of the International Space Station or something like that, the force of gravity is over 90% as strong as it is a bit over 90% strong as it is on the surface of the Earth. And that would hardly qualify for micro in my book. So while well-intentioned, I'm not a fan of that term either. Again, just call it what it is, and you won't go wrong. All right, in the next video, we will do a couple of examples of how to use Newton's second law of motion to analyze different kinds of force problems. Catch you in the next one.